In today's lesson, we are going to be looking at the volume and surface area of 3D shapes. So some of this might be review, but we're going to look at some different kind of concepts within volume and surface area. Keep in mind you did get a formula sheet with the previous lesson that gave you all the formulas for these shapes. Right? It should look something like this. Right? You did get this formula sheet. You will have access to this. So you don't have to memorize any of these formulas, but we will look at some kind of the main concepts of them. So first question, or not first question, but first idea, right? Volume talks about the amount of space a 3D object or substance occupies, right? So area was the amount of space a 2D object takes up. Volume is the amount of space a 3D object takes up. Surface area is the total area of the surface of a 3D object, right? And volume, we might want to add the units are cubed, right? So like meters cubed, centimeters cubed, feet cubed, things like that. And for surface area, because it's just another form of area, the units are squared. It's like meters squared, centimeters squared, feet squared. So we're going to be looking at these two concepts. So for example, the first question, a company makes a cushion in the shape of a triangular prism. The company wants to know how the amounts of fabric and stuffing will change if they make small and larger versions. The initial dimensions are shown below. Right? So we have this triangular prism. We have the area of the base. We have a length, and we have a length and a height, or you might say, so along those lines. So first, we want to determine the surface area. So we do need the surface area formula. So if we go to our formula sheet, we can see the surface area. Surface area is the first column. We see it's 2 times the area of the base plus the area of the rectangles. So in the formulas, you will see these different kind of breakdowns. So for the surface area, if we look at them, you see some of them, they are quite long. The main thing you want to focus on is the very last part, like this portion here. Oops, not all that. Just this portion here, or just this. Right? Because basically it's breaking it down, the area of each kind of surface, and then adding it up together. So for the triangular prism, it's 2 times the area of the base plus the area of the rectangles. So if I come back to my triangular prism here, if I were to unfold this shape, so to speak, right, I would have something that roughly looks like this. Obviously, it's just a quick sketch, but if I unfolded my triangular prism, it would look something like this. Now, the surface area is basically the area of all of these shapes. So if I unfold my 3D shape and lay it flat, what is the area that it takes up, or what is the area of all of the faces? Now, for the area of the base, we already know, or we're already given, that this is 390 centimeters squared. And it is an equilateral triangle. Even if we don't see it, it is an equilateral triangle. We're only given one dimension. Now, on your note, you do see this. It didn't transfer over to this, but we can assume, or I can tell you, that it is going to be an equilateral triangle. All sides are the same. So that means that this rectangle is 30 by 40, and so are all the other ones. Oops. So that means it is 30 by 40 for all the triangles, or all the rectangles. So the surface area is going to be 2 times the area of the triangles plus 3 times the area of the rectangles. And that's specific to this case because of the equilateral triangle. If it wasn't an equilateral triangle, then we would have different areas for the different rectangles. So 2 times 390 plus 3 times 30 times 40. go through, simplify it a bit, 780 plus 3,600. We get 4,380 centimeters squared. So that is the surface area of this shape. Right? Again, it is centimeters squared because it's area. So that is our surface area. Next, we want to find the volume. And again, we can go to our formula sheet and we have the volume, base times length times height divided by 2. And if we see on our diagram of the triangular base prism over here, right, we can kind of match up those dimensions with what we have. Now, if we look at our triangle though, the diagram we have, and draw in those lines again to show that it's equal, we don't have enough measurements to actually figure it out, right? We have the length, right? We have the base, we don't have the height. We could maybe determine it, but if we go back to our formula page, I'm just going to bring up that page entirely. If I bring up this, look at this formula page, volume is in this far right column, right? Let's look at the volumes of all of these shapes and see what we have. Volume equals area of the base times height. Volume equals the area of the base times the height. Volume equals the area of the base times height divided by 3. Area of the base times height divided by 3. Area of the base times height. Area of the base times height. So aside from the cone and the square base pyramid, which are two exceptions, right? Every other 3D object that we have, or that we can look at, or that we're given the formulas for, they all have the same formula. Area of the base times the height. And in general, that is what the formula for volume is, right? So the volume of any 3D prism or object or prism or cylinder is just basically the area of the base times the height. So if I can take this object and I imagine I stand it up, so the triangle is the base, then I can multiply it by the height, which in this case is 40. And the way you can think of it is, if I have the area, if I were to stack this, let me see how well my three-dimensional drawing skills are. So I have my my triangular prism. Right? And I basically, if I have the area of the base, I know this portion here. And if I know the height, that's basically, if I multiply the area of the base times the height, that's basically I'm finding out, I'm adding up every area, a slice every time, all the way up to the top. So basically I'm just adding a slice, adding a slice, adding a slice, or so on. So basically that is what we're doing to figure out the volume. So area of the base times height, this is going to be our general formula for volume in general. So as long as we can determine the volume, or the area of the base, and we have the height, we just multiply them together, which in this case we do. 390 times the height, which is 40, we get 15,600 centimeters cubed. Right, make sure because it's volume, it's cubed. The next question asks, what is the surface area and volume if the 40 centimeter length is doubled? So that means this length is going to be doubled to get 80. So our new length is now 80 centimeters. So what we're going to do is we're just basically going to calculate our new surface area and volume. The formulas are going to stay the same, right? We're going to have the area, or we're going to have 2 times the area of the triangles plus 3 times the area, 3 times the area of a rectangle. The volume is going to be the area of the base times the height. So when I go through, 2 times 390, the area of the triangle hasn't changed, plus 3 times, it was 30 times 40 when we originally did it. However, that length of 40 has now doubled to 80. Let me just move this over. So I have a new numbers to work with. So 2 times 380 plus 3 times 30 times 80. we get 780 again, plus 7,200. We get 7,980 centimeters squared for our new surface area. For the volume of this new cushion, we're going to take the area of the base, 390, times it by our new height, which is 80, and we get 31,200 centimeters cubed. So those are our new dimensions if we've doubled the length of this cushion. The next question now says, what are the area and what is the surface area and volume if the area of the base is scaled by a factor of 1.5? So now what we do, this is basically saying we've increased our area of the base by a factor, right? So it's kind of like doubling would be a factor of 2, things like that. Now that we do have to consider, because one thing, we are doubling the area, or it's scaled by a factor. The area is scaled by a factor. We're not saying that it's doubling, it's scaled by a factor of 1.5. So when we talk about a scale factor, we're basically going to be multiplying the area of the base. So our new area is going to equal our old area multiplied by the scale factor, but the scale factor is going to be squared. And the reason is that it's squared is because area itself is a squared unit. Area is a squared unit, that's why it's to the power of 2. So our old area is 390 multiplied by our scale factor of 1.5 squared, and we get 800, or if we break it down, 390 times 2.25 equals 877.5 centimeters squared. So if we're talking about a scale factor, we have to make sure that we adjust it appropriately to match what type of measurement we're dealing with. We're squaring it because we're dealing with area. If it was just the length, right, or if we're talking about the perimeter, right, we wouldn't have to square it because perimeter is a can't think of the term, right? It's maybe like a linear. Again, I can't think of the term, but it's to the power of 1. Volume we'll look at in the next one, and we'll talk about what we have to do with volume. So going back to this question, we do have our new area. So now what we can do is plug it into our old surface area formulas, which was 2 times the area of the triangle plus 3 times the area of the rectangles, because they're the same. And our volume is the area of the base times the height. So now we're changing, the area is changed, so 2 times 877.5 plus 3 times, going back to our original measurements, we forgot to do one thing. Area of the base is scaled by 1.5, so we have scaled that. But because the area of the base has been scaled by 1.5, all other measurements need to be scaled by 1.5 as well. So that was my mistake. So we need to go back and say 40 times 1.5 now, which gives us, no, sorry, not that. My mistake again. Because the area of the base has been scaled by 1.5, that means the length has to be scaled by 1.5 because that contributes, or sorry, the length of the triangle, because this contributes to the area. So 30 times 1.5 is now 45 centimeters. So new area, new length for the triangle, right? Original length for the prism. So that does change in our formula because now it will be 40 times 45 for the area of those triangles. 2 times 877.5, we have 1755 plus 5,400. In the end, we get 7,155 centimeters squared. And again, the reason we didn't square this factor is because it was it wasn't a squared unit, right? Length is a one-dimensional, so we didn't have to square anything. For volume, area of the base times the height, right? So the area of the base did change. We did calculate that. The height did not change. It isn't affected by the area or the changing of the area or the increase of the area. So 877.5 times 400, or sorry, times 40, 3,000 or 35,100 centimeters cubed. So that's what happens when we scale something by a factor, right? If it's just a singular unit, it's just a length, one-dimensional, we just multiply it by the value, right? Just if we were to double something, triple something, multiply by 2 or by 3. If we're dealing with a measurement or a value that is a squared unit, like area is a squared unit, or we have to put it to the power of 2. So that's why it's 1.5 to the power of 2. If you want to think of why, well, if we had the area of the base, or the area of a triangle is base times height divided by 2. So if I said, okay, let's increase it or let's scale it by a factor of 1.5, that means the base would be multiplied by 1.5 and the height would be multiplied by 1.5. So basically we're multiplying by 1.5 twice, or 1.5 times 1.5, or squared. So again, just kind of the reason. So because we're multiplying two values or two dimensions by 1.5, that is the reason that it's a squared unit. Or we square the scale factor. So next, what is the surface area and volume if all the dimensions are reduced by 25%? So this is similar to the last one, but because all the dimensions are reduced, or they're affected by a specific scale, I don't have to change specific dimensions. I don't have to recalculate anything. I just have to look at the overall surface area and volume. Right? So the original, I'm going to write down the original surface area was 4,380 centimeters squared, and the original volume was equal to 15,600 centimeters cubed. Now, because it is reduced by a factor, or reduced by 10 or 25%, we have to come up with what our scale factor is. So because it's reduced by 25%, what is left over? Right? What are we looking at, right? So in this case, if we're looking at reducing it by 25%, that's 100% minus 25%. That means we have 75% of our original amount, or as a decimal, 0.75. So that means our scale factor is 0.75. We have 75% of our original amount. So if I wanted to find what 25% less of each side length was, or each measurement, I would multiply it by 0.75. Now, because all the dimensions are reduced, I don't have to go and calculate the volume or recalculate the new measurements for everything, for the side lengths, for the area, and then recalculate the surface area and volume. I can go directly to the surface area and volume. So the new surface area, I'm going to take the original, the 4,380 centimeters, or leave the units out for right now, and I'm going to multiply it by our scale factor, 0.75, but the scale factor is going to be cubed, or sorry, not cubed, squared. Again, area is a square unit. So 4,380 times 0.75 squared, we get approximately 2,464 centimeters squared. The new volume be very similar. I take the original volume and I'm going to multiply it by the scale factor, but the scale factor is raised to a power of 3. And that is because we're dealing with volume, and volume is a cubed unit or measurement. So 15,600 times 0.75 to the power of 3, we get 6,581 centimeters cubed. So that would be our new volume if we reduce the dimensions by 25%. So this is just basically looking at how we can use scale factors to determine new volume or surface areas or different measurements, things like that, and just basically calculating volume and surface area in general. Next example, we're going to move on to looking at pyramids, because there are some kind of more unique characteristics or properties when looking at pyramids. So we want to figure out what is the volume of this pyramid, right? And its base, this Great Pyramid of Giza in Egypt, has a height of 138.5 meters, and its base is a square with sides 230.3 meters. We want to figure out what is the volume. And if I go to my formula sheet, I'm going to scroll up to a square base pyramid, but if I look at it, right, I see for a square base pyramid, it is the volume equals the area of the base times the height. So I'm going to write that down. The volume equals the area of the base times the height divided by 3. Now, I can figure out what the area of the base is, and this formula actually breaks it down further. We can see here, it does break it down further. In this next line, so I could say, well, because my base is a square, it is just going to be a side length, where they say b squared times h divided by 3. If this was a rectangular based pyramid, then we would do length times width times height divided by 3, and so on. 230.3 squared times the height, which is 138.5, divided by 3, works out to quite a large number. 2,448,591.8 meters cubed, because it is volume. That probably helps because you can see it a little bit better now. So base squared, because it's a square, so 230.3 squared times 138.5, all divided by 3. We get 2,448,591.8 meters cubed. And that is the volume of this pyramid. Now for the next part, the Great Pyramids were supposedly covered in sheets of white limestone. Assuming all sides were covered, how much limestone would be needed? So if I look at this, right, I have 4 triangles that are all the same. So I have 4 triangles. I'm going to make the assumption that they did not put limestone on the base, right? Because that is where they placed the stones. They didn't put anything underneath it. It was just sand or whatever is underneath the pyramids. So it's just the 4 outside faces, right, that I'm worried about. So I do need to determine the area. Now, if I was to look at one of these triangles, right, for the faces, I know the base, 230.3, but I don't know what the height is. Right? I don't know what the height is. I do have enough information to find it though. And you have to kind of think of the pyramid in 3 dimensions. Let's imagine we slice it right down the middle, right? We would see a cross section, something similar to this actually. So if I was to slice it right down the middle, so if I was to slice it, basically take this and go right down the middle and slice it in half, I would get a cross section, or I would see something like this. That's what I would see. That would be what the face that I see is. And I have the height now of this right angle triangle. So this was the face. This was the cross section. I have a right angle triangle. I have a height of 138.5. I don't know what the base is, but unique characteristic of a square base pyramid, the height will go right down in the middle of this. So this is actually half of the side length. So 230.3 divided by 2, which is 115.15. So with this, I can actually figure out that slant height, because I can use Pythagorean theorem, a squared plus, or sum of squares, plus b squared equals c squared. I have 115.15 squared plus 138.5 squared equals c squared. Square those, 115.15 squared plus 138.5 squared, get approximately 32,441.77 equals c squared, but I need to square root all of that. And I get approximately 180 for that side length, or that slant height. So that slant height actually now corresponds to the height of each face. So now that I know the height of each face, I can figure out the area of each side, or each face, or each triangular face. So the area of a triangle is base times height divided by 2. So 230.3 times 180 divided by 2. 230.3 times 180 divided by 2. 2,000 or 20,727 meters squared. But because I have 4 of them, I'm going to multiply this by 4. So 4 times the area of a triangle. 4 times 20,727. I get 82,908 meters squared. And this is the area that I'm looking for. So that is how much limestone would be needed to cover the sides of the pyramid. If I assume that they put limestone on the base, I could just calculate the area of the base and then add it to this area. All right. Last question. So a company produces paper water cups. Oh, that should be with. I don't know where the 2 came from. With a slant height of 1.9 centimeters and a vertical height of 8.4 centimeters. What is the capacity of the cup? So I need to find my cone formula. So if I go back to my formula sheet, I see my cone volume is on the far right, area of the base times height divided by 3. I see it broken down, but I can figure out the area of the base times the height. The base is a circle. I have the height. I'm just going to figure that out and then divide by 3. So if I look at my cone, I need to find the area of the base times the height, and it was divided by 3. The area of the base is a cone, or this is a circle. So the area of the base would be pi r squared. So pi r squared times height divided by 3. If I look at this, I have the height, but I don't have the radius. I don't know what the radius is. But I do have enough information to figure that out. I can figure out the radius because based off of my dimensions, I have a right angle triangle. So 8.4, 9.1, right? I'm going to use sum of squares, but I'm going to use the other one. So say a squared equals c squared minus b squared. A squared equals 9.1 squared minus 8.4 squared. Right? C represents the hypotenuse always. So 9.1 squared minus 8.4 squared. I get 12.25. I need to square root both sides. And I get 3.5 is my radius. Right? If I needed the diameter, I would just multiply it by 2, but I have my radius of 3.5 centimeters. Now I can use that in the formula, back into the volume formula. So pi times 3.5 squared times the height, which is 8.4, divided all by 3. 3.14 times 3.5 squared times 8.4 divided by 3, 107.7 centimeters cubed. So this cup will hold 107.7 centimeters cubed of water. Now for B, the company decides to switch to cylindrical paper cups with the same dimensions. How will the capacity of the new cups compare to the old ones? What is the new capacity? So if I'm looking at, I'm going to bring up my formula sheet again. Bring up just the sheet, don't need both. I'm looking at a cylinder and a cone. So if I have a cylinder and a cone, how do their formulas for the volume relate? Well, a cylinder says area of the base times height, it's pi r squared h. For a cone, it's area of the base times height divided by 3, and it's pi r squared h divided by 3. So it's almost exactly the same formula, except it's divided by 3. So looking at these two, if I have a cylinder and a cone that have identical dimensions in terms of the circle, the diameter, or the radius, and the height, the only difference is a cone is slanted and a cylinder is straight. The only difference in the formula is 1 is divided by 3. So looking at this, if I go back to my note now, a cone will have 3 times the capacity, oh, not a cone, sorry, going back. A cylinder will have 3 times the capacity of a cone of identical, or with identical dimensions, or with the same dimensions. So if I wanted to look at the formula, so volume is pi r squared h. For the other one, it is volume equals pi r squared h divided by 3. So again, this divided by 3 portion is why the cone is 3 times larger. So if I have a cylinder. So if I have a cylinder with these same dimensions, right? A height of 8.4, right? It would have a radius of 3.5. It wouldn't have a slant height. Provide a cylinder of same dimensions. I could go and calculate it, but I have all the information in the formula. So in this case, the new capacity would just be 107.7 times 3. We get 323.1 centimeters cubed. Right, so making the comparison between a cone and a cylinder, if they have the same dimensions, is very straightforward. You're just multiplying the cylinder by 3. Sorry, the cone by 3. If you had vice versa, if you had the cylinder and you wanted to find the cone, take the cylinder and divide it by 3 to get the cone. If we look at our formula, we do see similar connections with a square-based pyramid and a cube. Right? Similar idea. Right? Area of the base times height, area of the base times height divided by 3. The only difference is here, again, we're just dividing by 3. Right? So there are the same connections between a cube and a square-based pyramid. So we do see those connections between the volumes of some shapes. We focused on the cone. So again, a lot of different examples of volume and surface area. There's probably more that we can cover. This is some of the ones that may be newer, or maybe things that you haven't heard of before. Right? Finding the volume of regular shapes or even composite shapes is very similar to area of composite shapes. Break it down into the basic shapes that we know. So I didn't cover that too much or at all because I wanted to focus on some of the things that might be newer or a little bit more difficult.